Hello, everyone. Thank you very much for your interest in the MARVE project. In this session today, we are going to show a live demonstration of the MARVE framework. Let us mention a little bit about the flow of today's demo. We will feature two use cases from the GRN pilot in Malta related to traffic monitoring and awareness. First, we will explain the idea of the use cases, the motivation behind, and their relevance. We will then show you some details of the real-life setup in which the demo will be carried out, where and how the data is being captured in real time. And this is the very beginning of the data processing pipeline. Then, before showing you the user interface and the events that the platform is picking up in real time and how we visualize those, our idea was to show you also the behind the scenes part and how this is actually achieved by the platform. So we will show you a couple of backend components as well that deal with the deployment of services and data transformations. Then we will look at the end of the pipeline where we get the actual results in the user interface, how they are presented, a couple of traffic anomalies and traffic events that were captured, etc. With this, I hand over to my colleague Nicole from Green Roads, who will present the use cases and the real-life setup for the demo. Thank you.
Good morning, all. I'm Nicole from Green Roads Malta. We're a small SME aiming to provide smart AI-driven tools to help decision makers and businesses make intelligent, data-driven decisions in the domain of road traffic management and transport planning. Our country, where the use case is set, is currently experiencing a traffic crisis, with many people spending over 2 hours of traffic in traffic a day, and frequent nationwide traffic jams and traffic accidents. Other than the loss of quality of life for the citizens, this condition results in the loss of life through fatalities and pollution. Through discussions with various stakeholders, such as local transport authorities, NGOs, and citizens, we have identified 4 use cases to provide an AI-driven solution that can possibly address the previously mentioned societal challenges. Today, we will show you how the work was done with respect to 2 use cases. The first use case is traffic conditions and anomalous events, and this will be demoed today. Typically, the news of a disruptive event, for example queues following a vehicle collision, reaches the transport authorities after a series of messages sent by private citizens. This usually takes a considerable amount of time, especially if this collision is not considered serious. Thus, this use case aims to provide a real-time system that flags anomalous events to reduce the response time. This traffic condition detection allows the traffic control room personnel to respond to rapid changes in traffic conditions. These instances indicate that an anomaly has occurred outside the field of view of the camera. A useful feature that we have requested is the ability to view anomalies after they have occurred in the form of a video snippet. This tool allows for the analysis of minor anomalies that are the precursors to accidents, such as illegal parkings, after they have happened. The other use case that has been implemented is GRM4, Junction Traffic Trajectory Collection. This use case is focused on the requirement of long-term data analytics to shed the light on both the behavior of road users, example car drivers, motorcyclists, pedestrians, and so on, and gathering traffic statistics at road network junctions. This use case is of interest for long-term transport planning and evaluation. In particular, there is currently significant interest in studying active modes of travel, such as cycling, walking, and micromobility. For example, we can gather data on pedestrian activity that can then be used to study and plan pedestrian infrastructure, or else study bicycle behavior and highlight cases where there is a popular cycling route to update the infrastructure accordingly. For both use cases, we are making use of IP cameras with embedded microphone. These type of cameras were chosen for their reliability and robustness in the outdoor environment, but also since local councils and authorities are most likely to have similar equipment. Thus, the MARVE framework could be integrated with the already existing infrastructure costs. Both cameras are mounted at the sides of building. This allows such devices to be placed close to cameras, but still have access to shade and cooling, which was essential due to Malta's high temperature. As an edge device, a PC is used for dim jar location, providing anonymization. The anonymized stream is transmitted to the cloud to be processed by other components. The other cameras are streamed to the fog layer to be anonymized and then streamed to the cloud to be processed by SCDS and other similar components. You can see a simplified data flow on the screen. Various AI models and components are needed to complete these use cases. Maintaining and integrating all components is a difficult task. This is why the MARVE system was designed. Next, Manolis from Fort will explain how the MARVE system operates to maintain the impressive background required for these use cases. And with that, I will pass on to my colleague.
Sorry, there's a problem with PowerPoint. Share again. Okay. So, the main end user, considering the MARVE use cases, is the operator of the SmartVis decision-making toolkit, which constitutes the main front-end component of the MARVE framework. However, the operation of this front-end component depends on a very large set of software components that run in the backend of the MARVE framework. We would therefore like to demonstrate some tools that are used for the management and configuration of the backend part of the MARVE framework, which are addressed to the system administrator of the framework. In MARVE, there is a complex web of multiple interconnected components deployed on several different devices at the edge, fog, and cloud. We will demonstrate the MARVE tool to see how it can help to manage the complexity of configuring and deploying instances of these components to specific infrastructure devices. Furthermore, in MARVE there are complex data flows resulting from the need to deliver AI inference results from multiple components on multiple devices to SmartVis. We will demonstrate the Datana and DFB components to show how they can be used to facilitate the management and configuration of these data flows. So this is the login page of MARVE. All MARVE components are centrally deployed via MARVE, which is a Kubernetes dashboard for instantiating services as orchestrated containers. This is mostly for the technical users, such as the admins of the platform. The main elements of the layout are at the left side. One of them is the Images tab. Here we see all the Docker images that the users have uploaded. Any MARVE user can use any of these images to create and start a service. Next, we navigate to the Files tab. There are two kinds of files, private and shared. Private files are seen only by the logged-in user and no one else. Shared files can be accessed by any MARVE user. Under the Templates tab, all the YAML files necessary for the service deployment are listed. YAML files are based on Helm charts and include information such as target execution environment, edge fog cloud, exposed service endpoints, and resource restrictions. To clarify this a little better, we have templates that will instantiate a service at the edge, others to instantiate a service at the fog, and others at the cloud. All of this can happen through this dashboard. It is important to highlight here that it was very complex to combine all the different components of MARVE that needed to be deployed on different machines. MARVE made all this much easier because the technical users didn't need to worry about details like getting access to the machines and installing libraries, etc. All this is taken care of centrally from MARVE. For example, we see here audio anony component to deploy in UNS RPI, traffic analysis to deploy on GRN at the edge. By clicking on the Create button, the corresponding service is instantiated in the Kubernetes cluster. We will now find a user where the traffic analysis is running, which is CatFlow. Since I am an admin, I'm able to impersonate this user and view his services. We'll click Impersonate. So here we can see all the services that this user has created. Qbox is a tool that allows to see the current status of a service. So I will log in now to Qbox. So here we can see the two CAD flow instances that are running at the edge and at the fog. We can also see the logs here and here. And Qbox also allows us to access the service container too, like this. Next, we will show the Datana UI. Datana is run by Thomas Pariente from Atos, so I pass the floor to him.
Okay, hello. Allow me to share my screen. Okay. Yeah. Okay, I hope you can see my screen now.
Yes, Thomas, yes, we can.
Perfect. So, hello, this is Tomás Pariente from Atos. As Manolis was introducing, I want to show you one of the tools that help to manage and define and configure some data flows, especially for the data inference pipeline in MARVE, which is Datana. As you can see in this diagram, Datana helps on getting and transforming the data from the AI inference components to the smart data models that we adopted in MARVE, and moving the results from the edge fog to the cloud, and finally to the DFB, where the data will reside afterwards. These data transformation, as I mentioned, are based on the smart data models that are promoted by organizations that are dealing with smart data, such as the Fiber Foundation, TM Forum, OASC, or IUDX, as for instance. And the use of these smart data models makes the inference data stored in MARVE compliant with ADOT standards. So this is therefore easy to interoperate with in the future. So let me switch to the Datana user interface. I don't know if you see it, or I should share the screen. 1 second. Probably I should share the other screen. 1 second. Okay. I'm sharing now the Datana user interface, the main part of the Datana user interface. This is the one that is hosted in the Datana cloud. Is the Apache NiFi graphical user interface that helps somehow to define powerful and scalable data flows. So as you can see in the left-hand side of the image, of the graphical user interface, we have a couple of panels with the navigate panel that helps to navigate on the different aspects, so on the different parts of the graphical user interface, and the operational panel that helps also to do some specific operations, such as starting, stopping, or deleting some of the specific stuff that is in the graphical user interface. So in MARVE, we created different process groups, which is one of the units in Apache NiFi, for each of the different models to organize the data flows. You can see here, for instance, that we have a process group for VAT and AVAT, for SET and AT, ABCC, and some other aspect that we will see later. So this process group helped to somehow group the different data flows and organize them in a nice manner. So we show here the ones that are in the cloud. We have similar instances in the other layers, edge and fog, for the specific data flows that are running in each of the layers. So if we double click in one of the data flows, which, for instance, in this case, in the first one, which is AVAT VIA, what we see here is the actual layout of the data flow. So we can see this in this layout that we have divided this into different building blocks. The upper building block contains the processors that are consuming data from MQTT, which is the entry inference models to the TANA. Some processors validated data received afterwards. This is the second building blocks, where we have several processors that are handling these validations. And we have another building block that is handling at the right-hand side, that is handling the potential errors that happen and logging them in case there are some errors. And the most important building block, which is the transformation building blocks, which is this one, that somehow provides the possibility of, first of all, dividing the different type of events between alerts, anomalies, and media events, which are compliant with the smart data models that we mentioned before. And in particular, the transformation rules that are highlighted in this specific processor, that is the Jolt transformation processor. In this processor, just to have a look at the transformation rules, we can click here and basically see how NiFi proceeds to explain the transformation that are happening here, moving data from the input data to output data, and providing these transformation rules. Each of the components have different transformation rules because they have different inputs and output, different schema, and this has to be transformed to the smart data models, in this case for media events, that one. And the final building block is related to sending the data to a specific input port in the cloud that gets all the information from the edge, fog, and cloud, and send it to the next inline component, which is specifically the DFB. So this input port receives the data and pass the information to the Kafka or the DFB. So as you can see here, you see several numbers here. For instance, in this particular case, we are seeing that in the last 5 minutes, we have been sending several elements to the Kafka, so the system is up and running at this point. As you can see here, we can refresh and see how it works. So one thing that we can also stress here is that somehow this communication allows to also interact with the real-time data in NiFi. So this is not only for the definition of the flow, but also for the handling of the streams in real time. So we can see, as I mentioned before, this number of tasks that are happening in the last minute. But we can also do things such as starting or stopping the flow. For instance, I just stopped this publication. So right now, as you can see here, data is starting to be queued into the previous step, which also provides an overview of one of the main features from NiFi, which is that this allows not to lose or miss data, because the data, when something is stopped or you are doing some stuff, this is being queued in the previous step and allows you to basically being able to check the data. So we cannot even go to list the values in the queue and see what is happening at this point. Those are the elements that has been queued in the last since I stopped the data flow. And just by clicking on one of them, we can have a look of the specific information that we are talking about. The message in this particular case is an event from set, and this is the structure of the event that is going to be sent to NiFi, to the cloud, to Kafka. So we can restart the process at a given point of time, and you will see in a second that the queue is already emptied. So the data has passed to the DFB, and now the data can be accessed by a DFB. And this is what our colleague Tassos is going to explain right now, which the data that has passed to the DFB. So Tassos, the floor is yours.
Hello, this is Tassos Canelos from ITML. Hope you can see my screen. So I will demonstrate some features of the Data Fusion Bus component, or the DFB, which is developed by ITML and is part of the MARVE framework. As you can see in this diagram here, the Data Fusion Bus, illustrated with this big gray box, sits between the Datana component, which was just presented by Thomas, and the SmartViz component, which is the main front-end user interface of the MARVE framework, or the decision-making toolkit, which will be demonstrated after the DFB. So the main job of the DFB is to receive all the data from Datana and transfer it to SmartViz. But it does this in two main ways. On one hand, it makes available all the incoming traffic from Datana in real time to SmartViz by employing the Kafka messaging system. And also, in parallel, it takes all the incoming traffic and permanently stores it in a persistent storage repository based on the Elasticsearch technology. And so that then SmartViz can access this data asynchronously at any later date and access archived data for visualization purposes within the user interface. So what I will demonstrate right now is a tool that we have for the DFB administrator or any advanced user that wants to make any operations related to data management, data curation, or generally monitoring the data that is flowing through the Data Fusion bus and is being stored at the Elasticsearch repository. So this dashboard here is based on the Kibana framework, and it's basically connected to the Elasticsearch repository. So we can see all the data that is being stored there. Right now, we are seeing, for example, all the data from the audio tagging AI component of MARVE that has arrived in the last 24 hours or so. You can see this also graphically visualized here. These are this is the distribution of events generated by audio tagging that have arrived at the DFB, distributed across time here. For example, here you can also notice that during nighttime, these events were much fewer. The incoming events were much fewer than the ones that came in yesterday afternoon or earlier this morning. For example, also here in this last 24 hours, you can see that 7,329 events came in. But we can narrow this time window of reference. And for example, instead of the last 24 hours, maybe I want to have a look at the last 12 hours and see what's going on. Okay, as you can see, the events in this last 12 hours are significantly less. And we can, of course, narrow this even further. Maybe graphically here, I can select, for example, this time window since 9 a.m. this morning up to now. And I got 2,000 messages, for example. Okay, so right now I am seeing only the messages. I am isolating only the messages from audio tagging because we have configured the Data Fusion bus in a way that it has separate indices for the results of each AI component. And here I have a list of each AI component that is available to MARVE. And for example, if I want to look for results from other components employed in the GRN use cases, these are the data that I have from AVAD in the last hours, or from the sound event detection AI component, the text anomaly detection component, or for example, the cat flow component, which is a traffic analysis AI component. And this variant is responsible for detecting vehicles. So yeah, so in the last few hours, I have about 2,400 events from CatFlow regarding vehicle detection. And down here, actually, I have a full list of all these 2,400 events. I can select any one of these and look into it in all the detail that it encompasses. So you can see here, each document for each such event has a series of fields, and each one has a value. This one has particularly rich data, For example, I can see the lane in which the vehicle entered and in which it exited. I can see the speed at which it was traveling, and all sorts of data like this. I can also look at the raw form of the document, which is in a JSON format here. And another option I have is to look at all this data in a more tabular view. So I can add columns here. For example, I can add the ID of the camera that was used to detect this each vehicle, or the speed of the detected vehicle, or the name of the lane and which it entered. So this is what it looks like, and this is a kind of quick way of identifying some things. In fact, for example, regarding the ID of the camera, we are using 3 cameras in the GRN use cases. So I can also see the distribution of detections that occurred for each camera. So you can see here, for example, that camera 3, which is, I think, at the Zaytun location, detected more than the other 2 cameras, and camera 1, which is at the Mjar location, detected far less events. So going back, just to show one last thing, I can also make kind of composite queries. I can isolate events that come from a specific camera, for example. Yeah, from camera 1. And you would probably see now that, yeah, there are far fewer events associated like that. Or I can even filter out results by maybe I can just detect the ones that are traveling with more than 60 kilometers per hour. And you can see these are only 85 events that meet all these conditions. So this concludes the demonstration of this tool of the DFB. And then going back to this diagram, I will now pass the floor to my colleague Stella from Zilus, who will be presenting the SmartViz component. Thank you.
Hello, I hope you can see my screen. So I am Stella Markopoulou. I am a software engineer at Zilus, and we have created SmartViz, an advanced visualization toolkit. In the MARVE context, we have used SmartViz for the decision-making toolkit and configured it in its needs following the discussions and the guidance of the user requirements. For the GRN pilot, we will present 2 use cases, the GRN3, the traffic conditions and anomalous events, and GRN4, the junction traffic trajectories. Starting with GRN3. The first visualization widget that the user interacts with is a real-time map that holds real-time detected events by some of the MARVE's components. So each time a new event or an anomaly is detected by the inference pipeline, a pin pops up showing the total detected events in this location and the camera where these events were detected on. By clicking on the play stream button, the stream of that camera is played on the video stream widget below. So right now, we will see in a few seconds the stream from camera 2. Okay. So in this video stream widget, the user can also select another camera that he or she would like to see. So I will choose camera 1. And right now, I will be able to see on the screen the feed coming from camera 1. Going further down, we have two traffic speed detection widgets. Each one is depicting the lowest on the left and the highest on the right, recording vehicle speeds that are detected on the selected time period that you are seeing on the top of the screen. The vertical axis of the chart displays the speed of the vehicle in kilometers per hour, and the detected events are depicted as the vertices of the line chart. On the lowest speed line chart on the left, the detected events, as we can notice, are far less than the ones on the right, on the high-speed events. So this is normal because it is most common for a vehicle to speed up than slow down under a low threshold. The ones with interesting peaks are also highlighted, as you can see with these dots, to make the user recognize some of the most important events. If we would like to drill into these detections, as you can see on this line chart on the right, we have many events detected during the day on December 12. Then we have a peak right here at night with the vehicle speeding up to 108 kilometers per hour. And afterwards, we have less events due to the night hours. In the morning, the events are getting much more since there is more traffic and more passing by vehicles. We can also zoom in this line chart, and we can see an important peak right here with a vehicle detected speeding up to 143 kilometers per hour. Further below, we have the statistical data representation widget. We have several information depicted in this widget here. First, on this pie chart on the left, we have the percentage of the low and the high speed detected events as were depicted in the line chart above. We can notice here that indeed the most common detection between the two is the high-speed events with a percentage of 92.8%. So this confirms the logic that the most common events are the high-speed ones. Besides the percentages, the total amount of these events and the calculated average speed is also depicted below the pie chart. In the middle, in this infographic, we can see the detected pedestrians in this time period, which is the output of the CloudFlow component. On the right, we also have a pie chart depicting the traffic conditions events. This is mostly related to speed and traffic events, and these are the output of the audio tagging component. Finally, at the bottom, a table name detected vehicles information shows several detected types of vehicles. So the CloudFlow component that detected these events shows some information regarding some vehicles. For example, for the cars, we have counted 349 cars, and the most used entry and exit lane for the cars is the MGR westwards, and also the average speed of the cars is 46 kilometers per hour. Scrolling down, we also have two details widgets showing the available information of audio tagging, the CloudFlow and the traffic anomaly detection components. Informations like the starting time of the events, the ending time, the categorization of these events, the camera where they were detected on, and whether the user has reviewed or not these events are also depicted in these widgets. The toolkit also has some options for the user to filter and search through data. For example, I can change the camera. So right now, I will see events that were detected in camera 2. And also I can filter out some of the events. So as you can see here, where I type the motor in this filter option above the table, I can only see events that are corresponding to motorcycle events. So we also have an option of the verification and video requesting functionalities. So with this functionality, I can request from another component in the pipeline the video snippet that corresponds to this event and display it in the anomaly and event detection widget below. So this event is categorized as motorcycle, so by selecting it, we expect to see a vehicle that should be marked as a motorcycle event. And after confirming the validity of the detection, the user can give feedback back to the pipeline to give a review and verify it or not. So since this was indeed a motorcycle passing by, I will verify the validity of this event, and a confirmation that indeed my view was accepted by the pipeline will be shown to me. So moving to the next use case, the GRN4. So we first see the temporal representation of the detected events. The events are detected either by analyzing an audio stream or a video stream. The first rows, as you can see here on the left, which has as a name the vehicle name, are the output of the audio stream analysis, and the vehicle detected group on the bottom is the output of the video analysis stream. So the events are depicted either as dots on the timeline or as these boxes that show that this is a clustering of an event. The clustering means that multiple events of the same category have occurred so close in time that we grouped it. So by clicking on this cluster, you can see that these 4 events have spread out through time. Also, if I can hover on top of an event, I can see some additional information like the name of the component that has detected this event, the starting and the ending time, and the categorization of this event. Finally, it is important to note that each vehicle type is color-coded across the dashboard, and you can see their assigned colors on this legend on the top right corner of the timeline. Scrolling down, we have 2 details widgets showing the outputs of the sound event detection and the cut flow components. Following, we have the statistical data representation, and we have here information on the pedestrians on the left, and information of the detected vehicles and their behavior detected by the cut flow component. Following, we see the vehicle trajectories widget. This is a widget that is developed for MARVE, and it depicts the detected paths that the vehicle have made. The user can select from the filters bar the vehicle that he or she would like to visualize. So I will choose, for example, right here, bus, and I will see only the trajectories that have been made by buses. I can also narrow down the time frame and see far less events. And also, if I will toggle this animation button here and click apply, I will see how these trajectories will build up during time. Scrolling down, we have the final widget in this use case, the crowd density heat map, which depicts the probability of a pedestrian being detected in this camera stream. And it is drawn in a heat map on top of a static frame of this camera. The user can either click the play button and the available heat maps will be drawn in the static frame, as you can see, or I can move to the next heat map or the previous one in a more manual way. In this visualization, it's important to mention that the blue color here on the screen means that the probability of a pedestrian that is detected right here is 0. And the gradation from green to red means that the probability is increasing, with green being the lowest and red being the highest probability. And that brings us to the end of the SmartVis and the decision-making toolkit presentation.
We cannot hear you, Dagana.
Yes, thank you. Thanks a lot, Stella, and thanks a lot for your interest in the MARVE project and this live demo presentation.